What if a single click could shut down your city's power grid? What if hackers could take control of oil pipelines, water treatment plants, even nuclear stations, without ever setting foot inside? It's not science fiction, it's happening. And at the center of it all is SCADA. From giant factories to hidden control rooms, SCADA systems run the modern world silently in the background. But what exactly is SCADA? How does it control massive industrial machines remotely? And most importantly, how vulnerable is it? In this video, we're pulling back the curtain on one of the most powerful and exposed technologies you've probably never heard of. From real-life disasters to game-changing innovations, this system has seen it all. Stay with us till the end to uncover a real SCADA failure that nearly led to catastrophe, and how the industry is racing to stop it from ever happening again. SCADA stands for Supervisory Control and Data Acquisition, the digital nerve center behind modern industries. It's a system of sensors, computers, and interfaces that monitor and control industrial operations in real time, all from a central location. Imagine running a massive water treatment plant without stepping outside the control room. SCADA makes that possible, collecting data, automating processes, and allowing operators to react instantly to any issue. Without SCADA, industries would rely on slow manual checks, risking delays, errors, and huge costs. It's what keeps power grids running, oil flowing, and cities operating smoothly. But with this convenience comes complexity and vulnerability. To understand how it all fits together, let's break down SCADA's architecture. SCADA operates through 5 interconnected layers. Layer 1, field devices, sensors and actuators that detect changes and execute commands. Layer 2, RTUs and PLCs, controllers that collect data and handle real-time responses. Layer 3, SCADA server, the core system that processes data, runs logic, and issues commands. Layer 4, HMI, dashboards that let operators monitor, visualize, and control the process. Layer 5, enterprise systems, business-level software like ERP and MES that uses SCADA data for planning and decision-making. Together, these layers create a seamless system, from physical machines to executive insight, powering the industries we rely on every day. Let's break down the 3 most critical components of any SCADA system, the parts that physically connect machines to operators. RTUs, remote terminal units. RTUs are used to collect data from field instruments in remote locations. They gather sensor readings like pressure, flow, and temperature, and transmit them back to the central control system. They are often ruggedized to survive harsh environments and can operate on low power in isolated areas, like offshore oil rigs or mountaintop weather stations. PLCs, programmable logic controllers. PLCs are the decision makers at the field level. They monitor inputs from sensors and execute pre-programmed logic. For example, if a pressure sensor detects a value above the safety limit, the PLC can automatically shut off a valve. PLCs are ideal for high-speed, repetitive operations, such as controlling assembly lines or machinery in manufacturing plants. HMIs, human-machine interfaces. HMIs serve as the operator's window into the system. They provide graphical representations of the industrial process, gauges, alarms, and visual controls. Using an HMI, a technician can remotely view tank levels, start or stop pumps, acknowledge alerts, or even diagnose system faults. Together, these components form the core of how SCADA interacts with the real world, making the invisible, visible, and controllable. For SCADA systems to function, devices must communicate in real time. This is where industrial communication protocols come into play. They define how data is packaged, transmitted, and understood between systems. Modbus. One of the oldest protocols, Modbus is simple and reliable. It's still widely used in legacy systems and smaller networks. It works well in scenarios where you just need basic data exchange between PLCs and sensors. DNP3, Distributed Network Protocol. DNP3 is more advanced and is especially popular in the electrical utility sector. It supports time-stamped data, event logging, and more secure communication, making it ideal for critical infrastructure. IEC 61850. This protocol is built for electrical substations. It supports rapid, synchronized communication between devices and is built around object-oriented models, which make integration easier in complex power networks. OPC UA. A modern, platform-independent protocol that supports secure and encrypted data exchange across systems. OPC UA is often used when connecting SCADA systems to cloud platforms, AI engines, or enterprise-level dashboards. Each protocol has its strengths and ideal use cases. Choosing the right one is crucial for maintaining reliability, speed, and security in any SCADA deployment. Now that we've covered the tech, let's see where SCADA is used in real life. Water treatment plants. SCADA monitors water levels, pH, chlorine dosing, and pump operations in real time. It ensures safe, clean water delivery and prevents overflows or contamination events. Energy grids. SCADA systems balance supply and demand across entire regions. They detect outages, reroute electricity automatically, and coordinate with backup generators or storage systems. Oil and gas pipelines. Pipelines stretch thousands of miles and run through remote terrains. SCADA tracks flow rate, pressure, and temperature, alerting operators immediately if there's a leak or drop in performance. Manufacturing plants. SCADA ensures that production lines run smoothly. It flags bottlenecks, monitors equipment health, and provides data to improve yield and reduce downtime. SCADA doesn't just control machines, it keeps entire sectors running 24/7. Beyond real-time control, SCADA excels at collecting data over time. This is where Historian systems come in. Historian software logs and archives every data point, second by second. Think temperature readings, motor speeds, valve positions, everything. This data becomes gold for analysts and engineers. Operators use trend charts to spot patterns. Maybe a motor is vibrating more before it fails, or maybe energy usage spikes at the same hour every day. These insights lead to predictive maintenance, optimized workflows, and cost savings. With the rise of AI and machine learning, this historical data is now being used to forecast demand, detect anomalies, and improve decision-making across the board. But here's the dark side. SCADA systems, while powerful, are often vulnerable. Most were designed in an era where cybersecurity wasn't a top concern. They were isolated, offline, and physical access was the only risk. But as industries moved toward remote access and internet connectivity, the attack surface exploded. Real attack example, Ukraine power grid, 2015.
But one warning, the first known hacker-caused power outage has occurred. So thousands of people in the Ukraine left in the dark, literally, after hackers infected the country's electrical substations with malware. Cybersecurity expert David Kennedy with me now. He knows how they did it. So, David, how easy would that be to effectuate here in the U.S.?
Well, it's actually pretty easy. What we call the industrial control systems, or what actually makes power for our grid, is actually very vulnerable, and it's been documented for a number of years that there's been issues with our power grids.
Hackers infiltrated the control systems of multiple substations. Within minutes, power to over 200,000 homes was shut off. The attack wasn't just technical, it was strategic, using stolen credentials, malware, and even direct interaction with SCADA software. Florida water plant attack, 2021.
The search is on for a hacker who tried to poison a Florida city's water supply. Investigators say someone hacked into the water treatment system for Oldsmar, Florida. It's near Tampa, and it's unclear if the hack was done from inside the U.S. or not. The person increased the amount of sodium hydroxide to dangerously high levels. The supervisor saw the system being tampered with and was almost immediately able to intervene. Investigators say they have a few leads, but so far, no suspects.
A hacker remotely increased sodium hydroxide levels in the drinking water supply. Fortunately, an operator noticed and reversed the command, but the incident proved just how real the threat is. Common weaknesses: default passwords, open network ports, outdated software, lack of encryption, mitigation strategies, air gapping critical systems, using secure VPNs for remote access, regular audits and patching, intrusion detection systems, IDS, multi-factor authentication for operators. Cybersecurity is no longer optional. It's a requirement for any modern SCADA system. Let's look at two sides of the SCADA story. Failure: the 2006 Queensland water incident. A disgruntled contractor hacked into the Maroochy Shire SCADA system and released over 200,000 gallons of raw sewage into parks, rivers, and even hotel grounds. He used a laptop and radio transmitter to override pump operations. It took months to catch him and millions in damages to clean up the mess. Success: power grid optimization in Denmark. Using advanced SCADA combined with AI, a Danish energy provider optimized their renewable energy mix, balancing wind, solar, and traditional sources. They reduced power loss by over 10% and improved grid resilience during peak demand hours. These stories show both the risk and reward of SCADA systems. When misused, the results can be catastrophic. When optimized, the benefits are enormous. SCADA is evolving. The rise of edge SCADA brings computation closer to the source, enabling faster decisions without relying on a central server. This is especially useful in remote sites or when latency is critical. Integration with the Industrial Internet of Things, IIoT, is turning SCADA systems into smart ecosystems. Devices are becoming more intelligent, self-reporting issues before they happen. Cloud platforms now allow SCADA data to be accessed securely from anywhere in the world. This opens doors for AI, global analytics, and even mobile plant management. But with innovation comes responsibility. Securing SCADA in this new world is a race against time, and one that industries cannot afford to lose. SCADA is the silent force powering our modern world, from keeping your lights on to making sure the water you drink is safe. It's invisible, yet everywhere, powerful, yet fragile, and its future is unfolding right now.